In this video we're going to be looking at atmospheric pollution, so that is gases that are being emitted into the atmosphere as a result of human activity. So we're going to start off focusing on combustion. So there are two types of combustion that you need to be aware of. We have complete combustion, which is what we tend to talk about whenever we talk about combustion or combustion of fuels or combustion of fossil fuels. This is the type of combustion we're talking about. So you have a fuel, it reacts with oxygen, and it produces carbon dioxide and water vapor. Now, complete combustion can only occur if we have excess oxygen. Okay, excess meaning more than we needed. So, excess oxygen. And the carbon dioxide that is produced is a greenhouse gas, which means that it absorbs the long wavelength infrared radiation that's being re-emitted from the Earth back to space, and by doing that traps heat in our atmosphere. So, complete combustion of fuels requires an excess of oxygen. Okay, just means more than you need, and produces carbon dioxide and water vapor. The carbon dioxide is a greenhouse gas. Now, if you don't have enough oxygen, we have something called incomplete combustion. Now, incomplete combustion occurs when you don't have enough oxygen. There isn't enough oxygen to react with all of the molecules of your fuel. And as a result, you get some slightly different products. So there are a variation of things that can happen. So you could have your fuel, and it reacts with oxygen, but there isn't quite enough oxygen to form carbon dioxide. It instead forms carbon monoxide. And it still produces water vapor. Now, carbon monoxide is a toxic gas. Okay, it is colorless, odorless, and tasteless. You have no idea it's in the room. In the lab, we have carbon monoxide detectors on the wall, which automatically turn off the gas supply if the carbon monoxide gets too high. And the reason we have those is because in the science lab, we're going to be using Bunsen burners, and when a Bunsen burner is on a safety flame, it's carrying out incomplete combustion, which means that they're producing carbon monoxide. Now, in small amounts, carbon monoxide is not a problem. I mean, all cars produce carbon monoxide. Bunsen burners produce carbon monoxide. Most flames produce carbon monoxide. The problem is when you have a lot of carbon monoxide being produced in an enclosed space, like a classroom, that is more of an issue. So the reason we have the carbon monoxide detectors is if that carbon monoxide level gets too high, it turns off the gas, which turns off the Bunsen burners, which stops the production of the carbon monoxide. Anybody who has a gas fire in their living room will probably have a carbon monoxide detector as well as a smoke alarm. Anybody who has a gas boiler that's in a bedroom perhaps, rather than maybe an airing cupboard or the garage, if you have a gas boiler that's in a room that people live in, then that will also probably have a carbon monoxide detector, just in case something got blocked and not enough oxygen was able to get into your boiler. So instead of burning the gas in complete combustion, it started burning it incomplete, and that carbon monoxide was perhaps being produced, that alarm would go off to let you know, because there's no other way of knowing, because like I said, it's a colourless, tasteless, odourless gas, so you need a detector to find out that it's there. The other thing that could happen, if there's not enough oxygen, is your fuel will still combust, but this time it will just produce solid carbon and water vapour. Okay? And the term we give to this is soot. Now, the reason both of these reactions happen is because there's not enough oxygen. Now, importantly, it isn't no oxygen. If there was no oxygen, there'd be no reaction whatsoever. There is oxygen, there just isn't enough. And the easiest way to look at this is to look at a Bunsen burner. We have the collar on the Bunsen burner, and when we have that collar open, we're allowing oxygen in, and we get a very blue, very clean flame. That's complete combustion. You close that collar, you cut off the oxygen supply, you get a much less intense, very orange flame, because now it's carrying out incomplete combustion. That orange colour is caused by the solid carbon that's being produced, turning that flame that orange colour. So we basically have three main products that we need to talk about from combustion of fuels. If it's complete combustion, we have the carbon dioxide, which is a concern because it's a greenhouse gas and it absorbs long wavelength infrared radiation, causing global warming. If it's incomplete combustion, we have carbon monoxide, which is a problem because it's a toxic gas and it's colourless, tasteless and odourless. And carbon itself, soot, is a problem because it causes something called global dimming. If there's a lot of carbon, a lot of soot in the atmosphere, then what you can find is the light can travel smaller distances. So if you take an example, if you were to climb to the top of Mount Snowdon, so 2 different days you've climbed to the top of Mount Snowdon and you want to look at the view. Now on both of these days it is a clear sunny day, no clouds, but on some days you can see further than others. You might find perhaps sometimes when you've been to the coast, you can't see as far out to sea as you can on other days, and that is because of the carbon, the soot in the atmosphere, causing something called global dimming, which means that the light can penetrate a smaller distance through the atmosphere because of all of those solid carbon particles in the way. So the other thing that we need to consider as a byproduct of combustion is the production of nitrogen oxides. Okay, so nitrogen oxides are formed in combustion engines. So they are formed in the high temperatures inside combustion engines, like in your car. And at those high temperatures, the nitrogen from the air reacts with the oxygen in the air to produce nitrogen dioxide. And we need to balance that, two of those. Okay, so both of these are from the air, from the atmosphere, and it only occurs in the high temperatures caused in combustion engines. And the reason why the NO2 is a problem, the nitrogen oxides are a problem, is that they cause acid rain. So when those nitrogen oxides are emitted into the atmosphere, they react with the water vapor that is already in the atmosphere, producing nitric acid. So our NO2 that has come from the nitrogen and oxygen reacting in the high temperature of a combustion engine, that NO2 then reacts with the water vapor in the atmosphere, basically clouds. Clouds are water vapor, and the NO2 that's been produced in our combustion engine combines with the water to form nitric acid, and this is our acid rain. Now, nitrogen oxides aren't the only cause of acid rain. The other one is sulfur oxides. So sulfur oxides are formed by sulfur impurities in fossil fuels. Usually coal. Coal has a large amount of sulfur impurities. So coal-fueled power plants emit quite a lot of sulfur oxides. So these are formed because of the sulfur that's in the fuel. So if you've got a fuel and you're burning it, well, you're reacting it with oxygen. If your fuel contains sulfur, that sulfur will also react with oxygen, and it produces sulfur dioxide. And again, so we have sulfur from the impurities in the fuel. We have oxygen from the air, and we have sulfur dioxide being produced, which again causes acid rain. And it does that the exact same way as the nitrogen dioxide did. The sulfur dioxide that's being produced reacts with the water vapor already in the atmosphere to produce sulfurous acid. And again, that water vapor is from the atmosphere, that sulfur dioxide that's being produced from the impurities, the sulfur impurities in fuels, reacting with the water vapor in the atmosphere, this time to produce sulfurous acid. Now, the problem with acid rain is that when it rains and the acidity of that water is lower, it lowers the pH of soil, makes it more acidic. It lowers the pH of water, so rivers and streams, again, makes them more acidic. And also, it's going to start to corrode buildings and statues that are made from limestone. So anything that's made of limestone will corrode if the pH is more acidic. In terms of the waterways and the soil, a lot of organisms are very dependent on the pH of the water and the soil being a particular value. And there are huge forests in Scandinavia that have been lost because the soil pH has changed. Plants are lots of plants are very, very particular about the pH of the soil that they will grow in. And if the pH of that soil changes, then some plants are unable to adapt and will not be able to survive. So to summarize, we're going to use this multi-flow map. So we have combustion. What produces carbon dioxide and water vapor? That is complete combustion. And remember, complete combustion means excess oxygen. Water vapor, carbon monoxide, and carbon particulates. When they say carbon particulates, they just mean solid carbon, they mean soot. Okay, that is incomplete combustion. So if there is not enough oxygen, then you will start to get carbon monoxide, which is a toxic gas being produced. You will start to get solid carbon, soot or carbon particulates, which again cause global dimming. The production of sulfur dioxide is from sulfur impurities in fuel, usually coal, and our nitrogen oxides are from nitrogen in the air reacting with oxygen in high temperature combustion engines. Okay, and again, the sulfur dioxides and the nitrogen oxides, the sulfur dioxide dissolves into the water vapor in the atmosphere to produce sulfurous acid. The nitrogen oxides dissolve in the water vapor in the atmosphere to form nitric acid, and those are both acid rain. So the effects of these products. So the carbon dioxide is a greenhouse gas. Causes global warming. Carbon monoxide is a toxic, colorless, odorless, tasteless gas. Our solid particulates are soot. Okay, that causes global dimming. And our sulfur dioxide and nitrogen oxides, they cause acid rain. Here we have a question that looks at a possible link between air pollution and asthma. So we're looking at 4 different weeks. 2 weeks in 1990, 2 weeks in 1991. Now, during this week here, the 12th to the 18th of December in 1991, there was a peak in deaths and asthma-related deaths and visits to the doctor. So this question is all about sort of looking at it, and it also is kind of maths-based as well. So work out the mean number of deaths from all other illnesses during the 2 weeks in 1990 and the first week in 1991. So the first 2 weeks you got 1,200 plus 1,169 plus 1,166 divided by 3 to give us a value of an average value of 1178.3. So that is the average, 1178.3 deaths from other illnesses. How many deaths from other illnesses happened in London during the incident week? So during the incident week, it was 1,301. So we can see that that is above the average. How many extra deaths is this above the usual mean? So that was 1301 minus 1178.3 is 122.6 recurring additional deaths above the mean. Calculate this extra number as a percentage of the usual mean. So that is 122 122.6 over 1301 times 100 is an increase of 9.4%. So the deaths in that week alone, when there was an abnormally high amount of air pollution, the deaths were 9.4% higher. So does this evidence support the fact that deaths from asthma were unusually high in London during the pollution incident week in 1991? Now, importantly, this is the percentage increase of deaths from all other illnesses. So deaths from all other illnesses increased 9.4%. So if the percentage increase of deaths from asthma is greater than 9.4, then we can conclude that the pollution did have an increased effect on deaths. If it is the same or lower than, then we can conclude that it didn't, because the deaths increased 9.4% anyway. So now we just need to do the exact same process, but this time for the asthmatic deaths. So the average, if we work this out, so deaths from asthma were 70, 67, and 83. Over 3. So the average deaths from asthma was 73.3. In the incident week, there were 110 deaths from asthma. Okay, so that is an increase of 36.6. So all we've got to do now is work this out as a percentage increase, and then we can draw our conclusion. So 36.6, so percentage increase equals 36.6 over 110 times 100 is an increase of 33.3%. So if all deaths increased in that week by 9.4%, but asthmatic deaths increased by nearly 3 times as much, we can conclude that the increased pollution did cause a greater number of deaths from asthma. Okay, so the percentage increase in deaths from asthma was over 3 times greater than the percentage increase in all other deaths. Therefore, we can conclude that the increased air pollution caused more deaths from asthma by approximately, now remember, they increased by about 10% anyway, so that leaves us with about a 20% increase. So it increased by approximately 20%. The deaths from asthma in that week increased by approximately 20% due to the increased air pollution.